Welcome again. So, let us try to recollect where we last time stopped. That was, we were talking about geostationary orbit of a satellite. So, by definition, a geostationary orbit of a satellite will have satellite moving in the same direction as the Earth revolves, the orbital period of one sidereal day. It should be in a circular orbit, and orbital plane have a zero inclination angle with the Earth equatorial plane. Now, as we said that our Indian national satellites, INSATs, are all placed in geostationary orbit, or is called GEO. Let us see some more definitions of that. Let us assume this the sphere, Earth sphere, and this center of the Earth, and this is the equator, and a satellite is there. Now, this satellite, where it is, how do you define? There are many ways you can have a different coordinate systems and define where is the satellite, but very commonly used terminology is that this satellite to the center of the Earth, if we draw a line, at some point it cuts the Earth's surface. So, that is called sub-satellite point, as if somebody is looking from the satellite directly to the center of the Earth. Then on the Earth's surface, the line crossing there is called sub-satellite point, and from the sub-satellite point, if we towards the sub-satellite point, if from the satellite if we look, it is called nadir, NADIR, and from the sub-satellite point if we look at the satellite, it is called zenith. Okay. These two terms will come when we talk about the antenna. Now, the location of the satellite is defined in terms of sub-satellite point, latitude, longitude, a funny way, but this is very commonly used. That is, satellite locations are referred with sub-satellite point, latitude, longitude. And let us see for INSAT how it will look like. They say INSAT 4A is one of the 4th generation satellite, is at 83° east. Stop there. So, it talks about the longitude, it does not say there is a latitude, means it is a geostationary orbit satellite where latitude is 0, and its sub-satellite point is at 83° east on equator. So, INSAT 4A is a geostationary satellite, and sub-satellite point of INSAT 4A is on equator at 83° east longitude. It is on equator. Okay, here it is not shown that way. This satellite is not geostationary satellite. Just for your understanding, I have drawn it like that. But if it is INSAT 4A at 83° east, then 4A is a geostationary satellite, and sub-satellite point of INSAT 4A is on equator at 83° east longitude. Now, I am going to ask you a question, think carefully. A geostationary satellite at 87° east, and Kharagpur is 22° north and 87° east. The sub-satellite point will be right on Kharagpur, south of Kharagpur, north of Kharagpur, east of Kharagpur, west of Kharagpur, where? Think, and then you should answer. Don't look at the next part of the video and try to find the answer. Think. See, Kharagpur is north of equator, it is not at equator, and for a geostationary satellite, sub-satellite point is on equator. So, therefore, the answer will be from Kharagpur, sub-satellite point will be south of Kharagpur. Okay. Now, what will be the trace of sub-satellite point on Earth for a GSO? Now, it is not GEO, geosynchronous orbit satellite with non-zero inclination. We have seen that sidereal time and Earth satellite orbital period is same, then it becomes geosynchronous. But if it has a inclination, it is not geostationary. So, its subsatellite point will be moving. It is like this Earth, and this is the equatorial plane, and orbital plane is making some inclination, not zero inclination. Then the subsatellite point, Earth is revolving. How the subsatellite point will revolve? Take a atlas and then try to see where the subsatellite point of this is India, and let us say INSAT is somewhere here, and one of the INSAT is not geostationary. We have slightly changed it, made it geosynchronous. So, what will be the subsatellite point trace? You have to think and find out. Here I am going to show you, it is like a figure of 8. And for some other purpose, not a communication satellite, navigation satellite, Indian regional navigation satellites, some of them are placed in geosynchronous orbit, so that it moves top and bottom, that is from equator plane north and south, and exactly in 24 hours, exactly in a sidereal day, it completes this figure of 8. Okay. Now, there is another possibility, that is highly elliptical orbit, that is the inclination was non-zero, and there could be eccentricity non-zero, then it is a highly elliptical orbit. There are some satellites which are highly elliptical orbit, it is called Molniya orbit, which are used for mainly used by Russia, and some of them are, in this case the period is not full one sidereal day, is half of sidereal day, inclination is 63 degree, eccentricity is given, perigee and apogee heights are given. These are numbers taken from Molniya. So, there are some satellites which are used for highly elliptical orbit. Its purpose is different. We will concentrate our Indian purpose. Now, there are other orbits also. Approximately it is defined, that is low Earth orbit is approximate height is 1000 kilometers. There is no boundary, that is it has to be so and so orbit. Of this order 1000 kilometer is low Earth orbit. Medium Earth orbit is approximately 20,000 kilometer, around that, and geosynchronous orbit is approximately 36,000 kilometer, we have seen. So, these are very brief definitions of, we will use this term LEO, MEO and GSO and GEO, that is why I have shown this one. Okay, now, this is what we have seen about orbit briefly, but where is the satellite? It can be defined in terms of subsatellite point, but wherever you are on the Earth's surface, you have to put your antenna looking at the satellite, then only you will get the signal. So, you must know which direction is the satellite and how to look at it. Let us do some look angle understanding and calculation. So, here also certain common terminologies are used, which is called azimuth and elevation. This diagram is taken from internet from somewhere. Let us try to understand this diagram. I could not draw it properly, so just I will try to explain it here. Below this elliptical circle what I have drawn here, assume that this is a plane and a observer is standing here. So, below that there is the Earth, which is not drawn here. So, this plane, which is called horizontal plane, if you stand on the surface of the Earth, from your foot you just put a plane around the Earth that is tangent to the Earth. It is horizontal plane, it is called horizontal. This is drawn as a horizontal plane. Assume that this side is north, and this is horizontal plane, and there is an object in the sky, which is in this case satellite. So, the satellite to the center of the Earth, you draw a line, drop a line to the center of the Earth. It will cut this horizontal plane at some point. It is not subsatellite point. Subsatellite point, it is different, that is on the Earth's surface. It is on the horizontal plane, it will cut. If you draw a line from observer to this point, then the angle from the north towards the east is azimuth, and the angle from horizontal plane to the line joining observer to the satellite is elevation. The line joining the point which has cut the, which is going towards the subsatellite point. So, this line to the line joining from the observer to the satellite, this angle is elevation. That means you are looking from the horizontal plane, you are going up and looking towards the satellite, and also this angle has to be rotated from the north eastward. So, you orient your antenna eastward and you will again come to that line and you will get the azimuth. So, this is azimuth and elevation. In the textbook different diagrams are there, you can look at those and try to understand, but the main thing is understanding what is elevation and what is azimuth. So, the antenna has to be pointed skyward in angle of elevation and from the north eastward on the horizontal plane in the angle of azimuth. Okay. So, let us try to do some calculation. For that you may have to recollect the geometry and the derivations and other things. We need not go into that much detail. Our interest is to know that from my location, that is user location on the earth surface, how much distance away is the satellite, which direction I should look to the satellite, whether satellite is visible to me or not. Those type of questions will try to answer. So, therefore, some derivations we are not going, but certain definitions we have to understand clearly to do those calculations. So, let us do the spherical geometry calculation. Here again, azimuth is the angle from the north to the line joining the point created by the satellite to the earth center line on the horizontal plane with eastwise movement. I have explained this one. Okay. So, let us go to the next slide. Here I have drawn in another way. This is the earth, this is the center of the earth, and this is the equator on the surface of the earth. From the center of the earth station E, center of the earth we call C, and the satellite I call S. So, S to C, if I draw a line, Z is the point which cuts the surface of the earth. So, Z is the sub satellite point. Again, on the surface of the earth there is a station called earth station, I call it E. So, from E to the satellite, that is this length E s is the distance from the observer, that is earth station, to the satellite. This is important for us, because we will try to find out what is the delay for the signal to reach the satellite or from satellite to the earth station. And also these are the radius of the earth. Assuming earth is a sphere, C to E is the radius of the earth. Similarly, C to there are latitude longitude that will be coming. So, this is the longitude of the earth station called E, and this will be the latitude. Both are L. So, let us define small l for longitude and capital L for latitude. So, I will try to define RE as the earth radius, H as the orbital height, that is Z to S, D as the satellite range, that is E to S, small l E is the longitude of the earth station, that is small l E. This is the radius of the earth, C E. Then the distance from satellite to the center of the earth, SC or CS, is we call RS, which is CZ, that is RE, plus the orbital height, that is ZS. So, RS is equal to RE plus H. Then E to S is the distance from the earth observation, that is earth station to satellite. Longitude of the earth station, small le, is this particular angle, this assuming this is the meridian. Latitude of the earth station is this angle, and sub-satellite point longitude is small ls is this angle, and latitude of the sub-satellite point is capital LS is this angle. Now, in this process we have created a triangle, that is C, E and S, from where we can find out what is the distance d, that is our target for calculation. So, this C, E and S, we must have some angles which are defined inside. One of the angle is a gamma, let us define, which is called central angle, which is E, C to S, that is at the center of the earth, the angle created by this triangle. Then we have angle psi, which is C to E, that radius, to E to S, this line. This psi, if you think carefully, you will find that this psi is 90° plus, that is from the earth station. If we put a horizontal plane, it will be 90° with the center of the earth to earth station, and plus some angle. So, psi will be 90° plus that angle, which is nothing but elevation. So, let us put this diagram in a different way, remove the earth, and we are interested in this triangle where the C, E and S is there, and R S is equal to R E plus H, which consists of the subsatellite point. R E is C E, E S is D, gamma is the central angle, and psi is 90° plus elevation. So, in a triangle, we know to find out one side of the triangle, we can use the other two sides and the angle made by them, and those standard formulas are d square is r e square and r s square minus 2 r e r s and cos gamma of this. Now, if we take the r s square outside, then this same expression can be given as 1 plus r e square by r s square minus 2 into r e by r s cos gamma. Just r s square is taken out. We will see the implications of this. So, try to remember this particular triangle. This gives us lots of information. One of the information right now we are deriving is the distance from the earth station to the satellite D, and for which we must know what is the radius of the earth, assuming the whole earth is a sphere, and what is the orbital height, which is h. From there we can find out the distance from the center of the earth to the satellite, that is r s. So, to find out d, I need r e and r s, and also we need to know the angle gamma, right. Okay. Let us look at it. How do we find out the elevation? One uncertainty still remain, how to find out the gamma. We will see that. First, let us see that in this triangle again, which is C, E and S, and which forms a central angle gamma at C, and the sides are D, R E and R S. Using sine law, we can state that d by sine gamma, opposite side angle, is r s by sine of opposite angle, which is sine psi, which is nothing but 90 plus elevation. So, sine psi is sine 90 plus elevation, which is nothing but cos elevation, and by side changing you can find out the cos elevation is r s sine gamma by d. Simple triangle. Now, here we can replace d by r e and r s and gamma. So, cos elevation is r s by d sine gamma, and if you remember in the last expression we have taken out r s outside. So, that r s and the numerator r s gets cancelled. So, therefore, the expression becomes sine gamma by 1 plus r e by r s square minus 2 r e cos gamma by r s. So, in this case, for elevation, what is required? We need to know r e, radius of the earth, which is certain assumption as a sphere of the as assuming earth as a sphere, and r s, where we should know the orbital height. In case of geostationary satellite, it is known, and a cos gamma. and sine gamma. So, the gamma has to be known. Now, again in terms of latitude, longitude and the same triangle, the using some spherical triangle and law of cosine, straightway I am giving the expression. The derivations are available in the books. It will take time if we go on explaining the derivation. You can remember that cos of gamma in terms of latitude and longitude of earth station and satellite, the subscripts indicate whether if it is E, it is earth station, if it is S, it is for satellite, capital L for latitude, small l for longitude. So, cos gamma is expressed as cos of latitude of earth station multiplied by cos of latitude of satellite subsatellite point multiplied by cos of difference between longitude of earth station and subsatellite point plus sine of latitude of satellite subsatellite point and sine of latitude of a station. This is the cos gamma. So, you can find out gamma and you can go back to the previous expression and sine gamma and cos gamma values you can put and you will find what is the elevation. Now, one interesting thing that this is a generalized expression. So, for geostationary orbit we have said that subsatellite point is having no latitude, that is it is on the equator. So, therefore, Ls is 0, putting Ls equal to 0 here, you get cos gamma is equal to cos Le, cos of difference of longitude of earth station and subsatellite point. Now, this is to find out the distance and the elevation. For azimuth, okay, before going to azimuth, let's do some quick calculation. That is INSAT at 83 degree east, and I said here 0 degree north, but people do not say that. 83 degree east, that is geostationary satellite. Earth station at Kharagpur 78 degree east and 22 degree north. Find the earth station elevation angle to the INSAT. Since it is a geostationary satellite, you can put those numbers and find out the cos gamma as 0.92, and therefore gamma is 22.53, and you put cos elevation is the same expression and find out what is the number. So, for gamma you put this value 22.53, and for RE 6,378 kilometer approximately, and RS we calculated 42,164 kilometer. Find out what is the elevation. I am not giving the number here, these are simple calculation, but very interesting thing, you should look at it now. I have given an example with Kharagpur, and as you look at the map of India, Trivandrum or southern part of India is very near to the equator. What should be the elevation angle compared to let us say Delhi or southern northern part of India, which is away from equator? What should be the elevation? Which elevation angle will be lower? You can verify by putting some numbers here and doing calculation, but intuitively you can also say which elevation angle, whether it is a north of India is elevation angle will be lower than the south of India or vice versa for geostationary satellite, for INSATs let us say. Okay, you should do this your exercise and try to understand. Understanding is more important than just putting some numbers into formulas and getting some results. Understand this. Okay, now azimuth angle is a much more complex calculation. So, we will show you the results. There is the intermediate angle called alpha or A is found out first, which is in terms of latitude longitude as tan alpha is tan difference of earth station and subsatellite point longitude divided by sine of latitude of earth station. Some books give a different expressions for this, and derivations are there, all results are correct. I have taken this expression. So, now this intermediate angle alpha azimuth has to be found out with respect to alpha as where is the earth station. So, if the Earth station is in the northern hemisphere, that is above the equator, and the sub-satellite point is east of the Earth station, it is 180 minus alpha. If the sub-satellite point is west of Earth station, it is 180 plus alpha. If it is southern hemisphere, if the sub-satellite point is east of Earth station, it is alpha, and if the sub-satellite point is west of Earth station, it is 360 minus alpha. This table has to be remembered because geometrically it can be explained. I will try to do it briefly, but you can see. Let us see. So, let us say this side is north and this is the equator, this is the northern hemisphere, and your sub-satellite point is here, a station is here. So, the azimuth will be from north to this angle. Whatever alpha you find out will be 180 minus alpha. That means actually alpha is this side angle, which I have not drawn here. Similarly, if the sub-satellite point is west of the station in northern hemisphere, it will be 180 plus alpha. You can see from the north you come this way, 180 plus alpha. So, the alpha is angle like this. If it is southern hemisphere, same, that is azimuth is equal to alpha, and in the if it is a sub-satellite point is west of our station, 360 minus alpha. I tried to put it in books, you can search and find out the way of expression, but as a communication engineer, let us not worry much, we can use this standard formula for that. Now, let us see satellite how it is visible, whether it is visible to us or not. Now, this same triangle 0 degree inclination, let us say, that is our station is at 0 degree inclination to the satellite, then this RE by RS is equal to cos gamma. This is a right angle triangle. RE by RS is equal to cos gamma. So, to make the satellite visible, this RS should be greater than RE by cos gamma. This should be larger, far away. So, in case of geostationary satellite, cos gamma is equal to RE by RS. Put the numbers, you will get 0.1514, and from that you can find out gamma is equal to 81.3, and this angle from the satellite visible is 180 minus 90, this is 90 degree. So, 90 plus 81.3, which is 8.7 degree. Double of that is 17.4 degree. That means satellite with a 17.4 degree angle, it can see the earth end to end. So, the length of the coverage for the satellite visibility is this arc, that is Ez, that is Re into gamma. Re into gamma is this arc for anywhere in the satellite. So, visibility is a station at equator. If the station is at equator, it can see satellite. Let us say a station is at equator, it can see satellite in this direction, in the other direction. So, it is plus minus 81.3 degree from its own longitude. So, we can find out the station at 87 degree east. What is the geo visibility? GSO visibility or GEO visibility? 87 minus 81.3, that is 5.7 degree east to 87 plus 81.3, 163 degree east. So, that much distance it can see. And if it is a low Earth orbit, the number of satellite that is required is 360 divided by 2 gamma. How many satellites are required? That's so that you can have a continuous visibility around the plane. So, for the time is getting up, so we stop here and we will continue the discussion in the next session. Thank you very much.